Parametric equation and graph. If x and y are continuous function of t on interval I, then the equation x of t and y of t are called parametric equation, and t is called parameter. The set of points x, y obtained at t vary over the interval I is called a graph of the parametric equation. The graph of the parametric equation is called parametric curve or plane curve and is denoted by C. Sketch and identify the curve by the parametric equation. So first we will make a table value. We will choose the value for t and calculate the value for x and y. We go ahead and plot this point on the graph. Let's pick one more point. And so here we have the parabola. And the direction of the parabola as y increase is following this path. Now, we can also sketch the graph using a calculator. So how would we do that on the TI-84? So first we need to change the mode to make sure that it's in parametric equation. Then you will want to sketch the graph. So we put in the parametric equation t squared minus 2t and y1 is t plus 1. And take a look at the graph. And here we have a parabola. Let's change our window. Let's start t at say -10, max at 10, because I want to get the whole full looking graph. Okay, and let's take a look at the graph again. So here we have a parabola that open to the horizontal direction. So what is the curve that represented by the following parametric equation? So x equals cosine t and y equals sine t. So let's consider x squared plus y squared equal cosine squared t plus sine squared t equal 1 for t is in the interval 0 to 2 pi. Okay. So this is the equation of the unit circle. So let P be a point on the unit circle. So P is moving counterclockwise as t increase from 0 to 2 pi. Right, so that is the parametric equation of the circle. Now, I can use the same argument. I can say x squared plus y squared equal to cosine squared of 2t plus sine squared of 2t. This equal 1. For t is in the interval from 0 to 2 pi. Note that because we have a 2t here, the point P on that unit circle will complete the circle as t increase from 0 to pi. And P is also moving counterclockwise as t increase from 0 to pi. Now, the other part, as t continue from pi to 2 pi, P will complete another revolution around the circle. So what meant this here, the point P is moved around the circle twice. So in the first case, at this point P, with xy equal cosine of t sine t. Let's go around this unit circle only one time. But in this case, it will go around the unit circle twice. Now the next thing is, use decimal to sketch the graph of the curve. We enter the order pair of x and y, 1.5 cosine t minus cosine 30t, 1.5 sine t minus sine 30t. And we want t to go from 0 to 2 pi. So this is the curve that we get. I can screenshot this and put it into our paper. So that is the graph using decimal. The cycloid and other parametric curve. The curve traced out by a point P on the circumference of a circle. As the circle rolls along a straight line, is called a cycloid. If the circle has radius r and roll along the x-axis, and if one position of P is the origin, find the parametric equation for the cycloid. Now we suppose that we choose the parameter, the angle of rotation is theta of the circle. When theta equal to 0, where P is at the origin. Theta is 0, where P is at the origin. Suppose that the circle has rotated to a theta radian. Because the circle has been in contact with the line, we can see this picture here that the path being rolled out in this manner. This is the path of that point P. Okay. Well, then the distance OT, this distance here, is equal to the arc PT. When you roll that, you get this arc PT. The length of that arc. And the length of an arc equal R times theta, where theta is in radian. So then the center of the circle C is at the point R theta R. Let P, the coordinate P, x, y. Then here we can see that x is equal to the distance OT minus PQ. So that equal to R theta minus R sine theta equal R times theta minus sine theta. Y would then equal to TC minus QC. And that equal R minus R cosine theta equal R times 1 minus cosine theta. Okay, so the parametric equation of the cycloid are x equal R theta minus sine theta, y equal R 1 minus cosine theta. Now we were told that the radius of the circle is A. Okay, so then by this formula, then we can rewrite this. X is equal to A times theta or since we want to use the parametric equation, the parametric variable t, so we change this to A t minus sine t and y equal A times 1 minus cosine t. So that is the parametric equation of the cycloid. In our first step, where I say the distance OT equal to the arc PT, the arc that we're looking is this portion here, this green portion. This is this arc. There we go. Now, one of the first people to study the cycloid was Galileo, who proposed that bridges should be built in the shape of cycloid. John Bernoulli showed that the invert arc of a cycloid is among the possible solution curve to the Broughton problem. Now, if you don't know what the Broughton problem is, that it wants to find the curve along with the particle who slide in the shortest time only under the influence of gravity from a point A to point B. So what would the curve be? Now, the Dutch physicist Huygens also already shown that the cycloid is also the solution to the Torus-Kron problem. Well, the totochrons problem say no matter where the particle P is placed on an inverted cycloid, it takes the same time to slide to the bottom. Yeah. Next, we'll talk about the family of curve with parametric equation. Well, when x equal a plus cosine t and y equal a tan t plus sine t, what do these curves have in common, and how does the shape change as a increase? I'm not going to sketch this by hand because this will be almost impossible. So let's go ahead and see what happened when we sketch the graph using decimal. So first, let's see what happened. Let's graph this curve for a equal -2, -1, -0.5, and increase from there. We'll see what will happen here. Okay. So I start with, let's say, what happened when a equal -2. If a equal -2, my curve is -2 plus cosine t, -2 tan t plus sine t. And we want to sketch this from 0 to 2 pi. So that's our curve. Let's repeat this for -1. Again, from 0 to 2 pi. Right, so it seems like the it moved a little bit, and we have a little more pointy as it goes toward to the right. Let's see what happens when we have it closer to 0. Say -0.5. Oh, so now here we have a little loop. Okay. Let's repeat this. Say -0.25. Look like the loop is getting bigger. So we have a bigger loop. So what happened when a equal to 0? When a equal to 0, then the first term here is 0. So we have a unit circle. So let's see what happened when a becomes positive. Say positive 0.25. So the loop here now point to the left. And let's say what happened when it's equal to 1. Okay. So if you put it all back on, and let's just go from 1, and we'll take out the 0.5. So the curve is symmetric, right, for the -1 and 1, -2 and -2.5 and positive 2.5. You have a little loop, and then at this, when a equals 0, we have a circle in the middle. So when a is less than -1, both branches are smooth. But when A, as A approaches -1, the right brand acquire a sharp point, has a sharp point. At A approaches 0 to the left, the right brand now have a loop. At A equal to 0, we get a unit circle. Okay. At A approaches 0 from the right, the left brand now has a loop. At A approaches 1, left brand have sharp point. And at A greater than 1, both branches are smooth.